Let's take a look at a spring force. A spring is a great way of looking at a non-constant force, because we know when we looked at Hooke's law earlier, the more you stretch a spring, the greater the force that you have. If I stretch it this way, the farther I stretch it, the more the spring pulls back to the left. Also, we are kind of extending this a little bit so that if we compress the spring, it will push back to the right, and the more we compress the spring, the more it pushes back to the right. Now obviously there's a limit to that. If you compress it so much that the coils all collapse together, you can't really compress it much more than that without distorting the spring. But let's just imagine that we can compress it at least a little bit. Compressing it, pushing this, imagine that we've got a mass here, and we're going to push the spring to the left, compressing the, we're going to push the mass to the left, compressing the spring, and the spring is then going to push it back to the right. We're kind of arranging it that way to end up with a force in the positive direction. So the force will always be positive in this case for what we're going to look at. Let's imagine that we compress the spring from the equilibrium position where there's no force. We're going to compress the spring until our mass is now at some initial position x naught. And then we're going to allow the spring to push the mass back. We've got to be a little bit careful here and keep track about what force are we talking about. If I pull the spring this way, the force that I am applying by my hand, I am pulling that way in the same direction as the extension. But that's not the force we're looking at here. We want to look at the force that's actually being exerted by the spring. So if I pull this side to the right, the spring, although I'm pulling to the right, the spring pulls back to the left. Likewise, if I compress the spring, I'm pushing to the left, but the spring is pushing back to the right. So we've got to make sure that we are talking about the force that we want to be talking about. And the force that is involved here is the force from the spring. So what we're going to assume is that we take our mass at equilibrium when there's no force on the mass from the spring. We move the mass over here at some initial position x naught. Then we allow the spring, which is now pushing back this way, to move the mass back to the right to equilibrium. And we're going to assume that it's actually resting on a frictionless surface. So there'll be a normal force and weight, but they will cancel each other out. And so the only force, the net residual total force, is then just going to be the force from the spring. Now if we remember Hooke's law from before, F equals minus kx, we're starting out with a negative initial position. So we're going to say to the right is positive. So we're going to move it to an initial negative position. So x naught is a negative number. Let's keep that in mind. X naught is negative in this case. We compress the spring. X naught is negative. Putting in a negative here, the force is positive. So the force that's actually acting on the object is in this direction, which is then in the same direction as the displacement. So what's theta in this case? Theta would be 0. Cosine of 0 is 1. So we only have to worry about the multiplication of the force and the displacement. The cos theta just contributes a 1 to it. Well, let's try our integral formulation, and then we'll compare that to the idea that the work done is actually the area under our force curve. So let's try that. So what do we have? We have the work is equal to the integral from the initial position, which is x naught, to our final position, which is the equilibrium position 0, f sub x times dx. So what do we get? We have the integral from x naught to 0 of the force. What's the force? It's minus kx. Now the k, remember that's the spring constant. That's a constant. We're going to pull the minus k out front. So we have minus k and then x times dx. In other words, minus k and the integral of x dx. Now, remember the antiderivative. What's the inverse derivative of x? Well, To get x, we would have x squared. When we differentiate x squared, we end up with x, but we end up with that 2 in the front. So we're going to have to multiply by 1/2 to cancel the 2. This will be 1/2 x squared. There we go. And we're going to evaluate it from, from x naught to 0. What do we get when we evaluate it? We get minus k times, we put in 0 and we get 0 squared, 0, and then minus the evaluation at the initial point, 1/2 k x, oops, sorry, I took the k out, 1/2 x naught squared. There we go. Well, the 0 goes away. We have a negative times a negative, which gives us a positive, which is 1/2 kx squared. In other words, the work done by the spring is, x naught squared, is 1/2 kx naught squared. Wherever you put the mass, whatever displacement you have from equilibrium, and then release it, the amount of work to get it back to equilibrium will be 1/2 x naught squared. Now let's think about this. What if we had actually moved it over here so that x naught was positive? Well, positive x naught squared still gives us a positive number. Negative squared gives us a negative number. So the work is always positive. Well, why is that? Just remember that if we have a motion over here, the force is that way, and then the displacement is going to be that way as it moves back to equilibrium. In other words, theta between them is 0, a positive force. If we move this over here, the force is going to be negative, but then the displacement is also going to be negative. So again, the angle between them is 0, the work done is positive. So it doesn't matter if we move the mass to the left of equilibrium or to the right of equilibrium, we're going to end up with a positive work done. All right, great. Now, how does this correspond to what we would have gotten if we looked at it in terms of the area under the force curve? Well, let's draw that out and see what we get. I've drawn a little graph down here that exactly corresponds to the positions of the mass up here. We're going to start out with the mass at our initial position x naught. Now, what's the force on the mass? It's going to be in the positive direction, and it's going to have a magnitude of minus kx naught. X naught being negative, that's going to be a positive force. In other words, to the right, a positive force. So the force acting at x naught will be, the force is minus kx naught, which is positive because x naught is negative. As the mass moves closer to the origin, as x naught decreases, the force is going to decrease in magnitude linearly until when the position x is 0, the force will be 0. So our force is going to decrease linearly like this until we get to the origin. So that's what the force looks like from our initial position of x naught to 0. It's basically just a straight line. So what is the area under the force curve, the area under the force position curve? Well, it's a triangle. What's the area of a triangle? The area of a triangle is 1/2 the base times the height. In other words, 1/2, what's the base? The area of the base, or I should say the length of the base, sorry, is negative x naught. So remember, x naught is negative, so this distance would be negative x naught. Times the height. Now, what's the height? The height is negative kx naught. 1/2 base times height, 1/2 negative x naught times negative kx naught. What do we get? We get 1/2 k, the negatives cancel, x naught squared. So that is exactly what we just got when we looked at the integral. Okay, very, very good. Let's stick some numbers in here and see what we get. Let's imagine that we have a spring constant of 15.0 newtons per meter. And let's imagine it's a very, very big spring and our initial displacement, x naught, is negative 4 meters. So how much work is going to be done by this spring as it brings the mass back to equilibrium? what we have is the work is 1/2 times K, in other words, 15.0 newtons per meter, times x naught, which is -4 meters squared. We multiply that out and we get 120 joules. Or, again, notice newtons per meter times meters squared gives us newton meters, and we know a newton meter is a joule. Okay, very good. So the work done by the spring is 120 joules, and this must equal K minus K naught, the final kinetic energy minus the initial kinetic energy. But if we assume that our mass starts from rest, in other words, not moving, what is our initial kinetic energy? It's 0. So in this case, our initial kinetic energy is 0, and we end up with the final kinetic energy is 120 joules. All right, this is very interesting. Let's just think about this just for a second. The mass starts out at rest with no kinetic energy. The spring accelerates the mass by doing work on it. The amount of work done is 120 joules, and that 120 joules then goes into increasing the mass's kinetic energy. So now the mass has some kinetic energy, energy of motion. One way of thinking about this is the mass increases its kinetic energy. Where does that energy come from? Can we think of that? Can we think of energy as coming from someplace? Well, as a matter of fact, we can. We can think of it as the mass had some stored energy in it. As we initially move the mass from equilibrium, we are doing work on the mass. We are doing work on the mass in this direction by compressing the spring. So we've kind of done work on the mass, and that energy is now stored in the mass and the compressed spring. So that when we release it, the spring moves the mass back, it accelerates the mass, moving it back to the equilibrium position. In some sense, releasing that energy, turning that stored energy into energy of motion. Well, stored energy we call potential energy. This is another kind of energy. We've seen kinetic energy, which is energy of motion. Objects in motion have energy. But there's also potential energy. We can think of this as stored energy. Somehow it's stored up somewhere. In the case of the spring, it's stored up in the compression of the spring. Perhaps there are other kinds of stored energies. Well, we'll see. And we will write potential energy sometimes as PE for short, also sometimes U, traditionally U rather than P, which is actually used for something else. Capital U is used for potential energy. And what is happening in this case is that the potential energy is being converted into kinetic energy. And the total amount of potential energy that's lost is exactly equal to the work done, which is 120 joules, and that goes into the object's kinetic energy. Okay, we're going to see more of that later on. What I'd like to do now is to see if we can't generalize our definition of work even more. We've looked at one-dimensional work when we have a constant force. We've looked at one-dimensional work, just a single direction of the force and the displacement. When we have a varying force, and we've seen how we can deal with that, what if we have a general three-dimensional force and a general three-dimensional displacement, and the force is not constant? How can we deal with that? How can we really generalize this definition of work? Well, what we're going to do is we're going to take a look at a general way of manipulating vectors, similar to what we've been talking about. We're going to take a look at a general approach to vectors and then see how this can be used with our definition of work.